الأوسط وتمكينهم بعلوم الفضاء والتكنولوجيا. طبعا نحن سعيدين اليوم بأنه نرحب بطلابنا اللي بتركيا، وفي عنا طلابنا أيضا بالأردن، طلابنا بلبنان، وكمان بنرحب بشركائنا وبأصدقاء فينيكس سبيس. بشرفنا اليوم انه يكون معنا الدكتور ديان ميخالوف، راح يقدم محاضرته عن الثقوب السوداء، وكمان راح يجاوب عن اسئلتكم بعد المحاضره. الدكتور ديان حامل شهاده دكتوراه بالفيزياء الفلكيه بجامعه كامبريدج، وحاليا باحث ما بعد الدكتوراه بمعهد ماكس بلانك لعلوم فيزياء الجاذبيه. قبل ما نبدا بس راح احكي لكم كيف راح تكون المحاضره اليوم. راح تبدا المحاضره هلا بعد بس اخلص انا راح تبدا المحاضره، وراح يكون الدكتور ديان عم يعطينا المحاضره من خلال فيديو مدته اقل من 30 دقيقه، وبعدها راح يكون معنا الدكتور ديان راح يجاوب على الاسئله. فبس يبدا الفيديو وانتم عم تشوفوا الفيديو، اي اسئله بتخطر على بالكم عن الموضوع فيكم تكتبوها على الشات، فيكم طبعا تبعتوا لي اياها خاص على الشات او تكتبوها على عام. طبعا بعد ما نحط الاسئله بنجاوب عليهم مع الدكتور ديان. الندوه طبعا هي راح يتم تسجيلها وراح نشارك الرابط معكم لاحقا. كمان بس بحب اقول لكم انه راح يكون في بالفيديو ترجمه تحت باللغه العربيه، فحاولوا انتم تجهزوا شاشاتكم بحيث تقدروا تشوفوا الترجمه، بحيث ما يكون في عندكم مثلا اي شريط باسفل الشاشه. ممكن لو كنتوا عم تشوفوا على اللابتوب فيكم تكبسوا كبستين على الفيديو فبيصغر الفيديو اذا كان في شيء بيعيق تشوفوا الترجمه. وهلا بقى رح نبدا الفيديو. So the video is starting now.
My name is Dan Mihaylov, and today we are recording at the Albert Einstein Institute for Gravitational Physics. Now, in order to help you understand what black holes are and why they're so interesting, we need to go through several topics. First, I'm going to explain to you what this term means and what black holes are. Then we're going to speak about some of their properties. And finally, we're going to discuss the observations of black holes and what is the evidence for them in the universe. Now, before we talk about black holes, there are several fundamental concepts that we should revise. And let's start with our understanding of the theory of gravity. The story begins more or less with Sir Isaac Newton and his theory of gravity from the 17th century. What Newton said is that the force of gravitational attraction between two bodies is proportional to the masses of these bodies and inversely proportional to the distance between these two bodies. And this was absolutely revolutionary because no one so far understood how exactly gravity behaves. So this was a fundamental improvement in our understanding of gravity. Now, it turned out later that Newton was only partially right, and Einstein provided a more complete picture of our understanding of gravity. What Einstein said in his theory of general relativity is that what Newton said, is only a partial understanding. And in fact, the full story is that geometry of space-time in our universe can be related to the distribution of mass and energy in the universe. The last thing that I would like to mention at this point is the concept of escape velocity. This concerns the fact that you need to be moving at a fast enough speed in order to escape the gravitational acceleration of a body. All of us have seen rockets taking off from Earth and reaching space. And even though we see how the rockets take off vertically, the vertical speed and acceleration is not what matters. It's the horizontal speed and acceleration that is what matters in order to get that rocket to reach space and stay there. They have to reach a certain very high velocity around the Earth in order to be able to escape the gravitational attraction. The next thing that we should mention is about the speed of light. Now, even though the speed of light is very high, it is only finite. And not only that, but it has been discovered that nothing in the universe can move faster than the speed of light. To help you imagine how fast the speed of light is, it only takes 8 minutes and 20 seconds for light to reach us from the sun to the Earth. It only takes 2.5 seconds for light to reach from the Earth to the moon and back. And inside 1 second, light can make 7.5 trips around the world. So if you send an object which moves at the speed of light around the Earth, in an orbit around the Earth, in 1 second, it will circle it 7.5 times. That's how fast light is. Let's talk about black holes. Black holes are, in their essence, objects which have become so heavy and dense that their escape velocity, that we just talked about, has become larger than the speed of light. What this means in practice is that nothing, not even light, can escape these objects. And that's why when we look at them, we basically see a black body, because there's no light originating from it that we can see. That's what we call a black hole. Now, black holes don't have a definite surface like planets or stars do. What we see when we look at a black hole is the so-called event horizon of the black hole, which is an imaginary surface that once you cross it, you will fall into the black hole. There is no way to escape the gravitational pull of the black hole if you get closer to it than the event horizon. Let's talk about how big and heavy black holes can be. The masses of black holes start from around several solar masses and go up to tens of billions of solar masses. So there is a very big range of masses for black holes. But what is important is that even a black hole that is several solar masses can be condensed in a size that is several tens of miles across. Because there is such a variety of masses and sizes, scientists have started to classify black holes according to their size. Small black holes that are no more than, say, 10 solar masses are called low mass black holes, and they are usually very compact, so they can be very small objects. The really big ones that are several tens of billions of solar masses are called supermassive black holes. And we also have anything in between that we call intermediate mass black hole. Let's talk a little bit about the masses and sizes of black holes. Now, when we talk about how massive a black hole is, we usually measure it in units of solar masses. So we say how many solar masses is the mass of a given black hole. Now, the mass of the sun is about 2 times 10 to the 30 kilograms. So that's 2 and then 30 zeros after that kilograms is the mass of the sun. And the lightest black holes start at several solar masses. The heaviest black holes go up to tens of billions of solar masses, and those are really, really massive black holes. In terms of sizes, the smallest black holes could be very compact objects. Even though they pack several times the mass of the sun, they could be no bigger than maybe several tens of kilometers across. The largest, most massive black holes can grow up to be much larger than the size of the solar system. So we have a big range both in the masses of black holes and their physical sizes. The reason why scientists have classified them in these categories is because they differ in the way that they form as black holes. Low mass black holes usually form as the product of stars. The reason that a star shines so brightly is because there are very intense thermonuclear processes inside the star which produce all this light. But at a certain point, a star runs out of fuel and several things can happen. It could explode as a supernova. It could become a giant and slowly die away, or if it is massive enough, if it can collapse onto itself after it expends its fuel. So what happens is that literally the star, after using up all the fuel, collapses onto itself and condenses into a very small region of space. And that is how a black hole forms. Who came up with the idea of black holes? Even back in the 1800s, people theorized about possible objects which are so heavy that their escape velocity is larger than the speed of light. Einstein later on confirmed that they can exist within his theory of general relativity. But even after that, it took several more decades until we got the first observational evidence of black holes. The way in which we detect the presence of black holes is also very interesting because, as you can imagine, it is very challenging to detect an object which doesn't emit any light. Now, the way that we establish the presence of a black hole somewhere in space is by observing the stuff, the matter that orbits this black hole. For example, the black hole at the center of the Milky Way, Sagittarius A star, this is what we call a quiescent black hole. It means that as opposed to an active black hole, it has stopped accreting matter from the surrounding bulge of the Milky Way. This black hole is what we call a quiescent one, as opposed to an active supermassive black hole, which still accretes matter from the galactic bulge surrounding it. Sagittarius A star doesn't do that anymore, so we cannot even see a disk of gas surrounding it. But what we can observe are the orbits of stars just around the black hole. And from the orbits of these stars, we can calculate the mass of the object that they are orbiting, and we can measure the radius of that orbit. And if we calculate how much mass is contained within that diameter of space, we can establish that the only possible explanation for that object is that it is a black hole. I can erase it again. Another way to know that there is a black hole somewhere in space is by observing its effect on other celestial objects that are directly behind it. For example, if we are looking in a certain region of space and we notice two copies of the same star at two different positions, what we can realize is that this is not the same, these are not two separate stars, but it is the same star, and the light coming from that star has been disturbed by a black hole, which has produced two copies of the image on two different points of the sky. Even more interestingly, we have now discovered black holes merging, collapsing together and becoming one black hole. And since 2015, we have the means and the technology to detect these mergers of black holes and listen to the gravitational waves produced by them. Even more interestingly, we have also detected the collision and merger of two black holes to produce one. And in this process, we have also detected the gravitational waves that were produced by this merger. The gravitational waves are actually a direct consequence of Einstein's theory of gravity, according to this equation. If two black holes were spinning around each other and about to merge, this directly translates to ripples in space-time, much like the ripples in a pond if you throw a rock in it. And since 2015, we have the technology and the means to detect and analyze these gravitational waves. These gravitational waves have actually provided us with a wealth of information about the black holes, because each time that we detect a gravitational wave, we actually can study three black holes. The two black holes that merged together and the black hole that was produced by the collision. And by analyzing the data from these gravitational waves, we can learn about the masses of the two black holes and the third one that was produced. We can measure the spins of the black holes, that is, how fast each black hole was rotating around its own axis, much like the Earth rotates around its own axis. We could also measure how long it took for these black holes to merge, and we can understand how far away from us this happened. As an instance, the first pair of black holes that we detected merging, this actually happened 1.5 billion light years away from us. What this means is that the signal from this collision, which by the way travels at the speed of light, took 1.5 billion years to get to us. So it happened 1.5 billion years ago. And this was around the time when the first cellular, multicellular organisms were forming on Earth. Even though over the past century we have learned a great deal about black holes, there are still a number of open and unresolved questions about them. The most interesting and pressing of them is what happens inside a black hole? What is there inside a black hole past the event horizon? Now, we know that at the center of a black hole sits the so-called singularity, which is where you eventually end up if you fall into a black hole. However, what is the internal structure of a black hole is still a very open and interesting question. An interesting aside here is what happens if one falls into a black hole. Now, because of the very strong gravitational forces that act upon you as you fall into the black hole, what happens is that you would gradually be stretched in one direction while at the same time squished in another direction. So you would gradually become very thin and very long, much like a piece of spaghetti. That's why this process is actually called spaghettification. Now, this would eventually result in your unfortunate death as your limbs and other body parts are ripped off from you. But unfortunately, this is what happens when one falls into a black hole. Another open question concerns the areas of the event horizons of two black holes as they merge. Stephen Hawking, the famous British astrophysicist, proposed a theory about the event horizons of black holes as they merge. But this theory also left a number of unanswered questions that we are still trying to resolve. Another issue, a very interesting open question, is what happens to information as it falls into a black hole. Since a black hole is uniquely described by three parameters, its mass, its spin, that is how fast it rotates around its own axis, and its electrical charge. This means that any information about any body that falls into the black hole is inevitably and irretrievably lost. Now, this goes against some of our established notions about physics and information theory. And therefore, this is a problem that me and some of my colleagues here at the Max Planck Institute are trying to resolve. I first became interested in physics and astronomy when I was very young, maybe 4 or 5. And I started asking questions like, how big is the universe and how come the universe is infinite? And I realized that the answers of these questions that I received back then did not fully satisfy me. And I decided that it would be really cool if one day I can contribute to our better understanding of the universe and what happens in the sky very far away from us. In order to become a physicist, the most important quality is to be curious. If you're curious about the world around you and you want to get a better understanding of it, everything else will come naturally. You would have to learn a lot of new concepts. You would have to study mathematics and physics, but eventually you have all the tools that you need in order to work and excel as a scientist.
Thank you for watching. We're pleased to have you here with us today, and we'll start Q&A session with Dr. Dian. شكرا للمتابعة، شكرا لحضوركم اليوم. رح نبدأ هلا بالأسئلة مع الدكتور ديان. Dr. Dian, thanks for being with us today.
Thank you very much.
Dr. Dian, I have a couple of questions here.
Wonderful.
So we'll start with the first question. The question is our sun going to turn into a black hole? So the question in Arabic. السؤال إذا هلا أنا راح أسأل الدكتور ديان أسئلة. فسألته هلا أنا السؤال الأول إنه هل ستتحول شمسنا يوما إلى ثقب أسود؟
Okay, very good question. So is our sun going to turn into a black hole? The answer is no, because our sun is not heavy enough to become a black hole.
Thanks, Dr. Dian. So الإجابة هي لا، الشمس ما راح تتحول لثقب أسود. السبب إنه الشمس ما هي ثقيلة بشكل كافي، لازم يكون في كتلة معينة، فكتلة الشمس صغيرة وبالتالي ما راح تقدر تتحول لثقب أسود.
What will happen to our sun is in several billion years, it will turn into a red giant. It will become much larger and it will actually become so big that it will envelop the Earth itself.
It will explode?
It will swallow up. It will become larger and larger until it becomes so large that the Earth will fall into it.
Oh. اللي راح يصير للشمس بعد عدة ملايين من السنين انه راح تتوسع وتكبر وتتحول لشيء اسمه العملاق الأحمر. هذا اللي راح يخلي يعني الشمس تبتلع المجموعة الشمسية. I might start with the second question.
Yes.
Okay, so we have an interesting question here. What is the final destination of a black hole? Do they like die out, or like for stars, the stars will die out and turn maybe to a black hole, or like or something different? But what about black hole? Do they end?
Very interesting. Thank you for this question. So depending on their masses, there are different things that could happen to a black hole.
طيب طبعا السؤال كان انه شو ممكن يصير بالثقب الاسود نفسه. نحن شفنا انه النجوم هي عم تتحول لثقب اسود، فالثقب الاسود بعدين هل راح يموت الثقب الاسود؟ شو بيصير فيه في النهايه؟ الجواب كان هذا بيعتمد على عده عوامل. Back to you, Mr. Dian.
Some small black holes actually can evaporate. There is a process called Hawking radiation, which allows matter and radiation to be emitted from a black hole through a very special process.
All right. في عم بيقول هذا طبعا بيعتمد بقى على نوع الثقب الاسود. هلا في ثقوب سوداء ممكن في النهايه تتبخر. فالثقوب السوداء هلا هي عمليه التبخر هي عمليه لها علاقه بحجم الثقب الاسود، وهي العمليه بتسمح للمواد داخل الثقب الاسود انها تتبخر منه. Back at you.
For larger black holes, the answer is that we simply don't yet know, because we have only known about black holes for less than 100 years. And these objects go on to live for tens of thousands of years, maybe even more. So we don't yet know what happens to all black holes. Some of them might evaporate, or something else might be happening to them in the universe. They can merge to produce, they can merge with another black hole to produce a third black hole. They can merge with stars and eat them up and swallow them, or something else that we haven't yet discovered.
الحقيقة إنه الجواب لهذا السؤال إنه شو راح يصير بالثقب الأسود نحن لسه ما فينا كثير نعرفه، لأنه نحن معرفتنا بالثقوب السوداء جديدة. يعني نحن اكتشفنا أو عرفنا شيء عن الثقوب السوداء بحوالي بس ال100 سنة الأخيرة، بينما أعمار الثقوب السوداء بتكون أكثر من 10,000 سنة ممكن. فاللي نحن بنعرفه مبدئيا انه في عنا عمليه اسمها التبخر، في عنا ممكن انه الثقب الاسود يندمج مع ثقب اسود ثاني، ممكن الثقب الاسود يندمج مع نجم. Back to you, Mr. Dian.
And that's the answer.
That was the question. Okay, so I might proceed to the next question.
Let's proceed.
All right, so has anyone got close to a black hole? I'll say the question in Arabic. في حدا قدر يقرب أو هل قدرنا إنه نكون قريبين جدا من الثقب الأسود؟
No, unfortunately, no one has gotten close to a black hole, at least no one from Earth. We know that they exist. We know that there is a black hole at the center of our galaxy, but so far we can only study them from a distance.
لحد الآن ما حدا قدر يقرب من ثقب أسود. نحن بنعرف إنه هن موجودين، بنعرف إنه في واحد بمركز المجرة، بس لحد الآن نحن ما قدرنا نكون قريبين من أي ثقب. So I think this is the answer, right?
Yes. Yes.
Yeah. Okay. So I'll go to the next question. I have a question here about a picture of a black hole. So the question is like, how were the scientists able to take a picture of a black hole? Is there something like that?
There is indeed a picture of a black hole which was unveiled last year.
طبعا السؤال هون نحن رحنا على السؤال اللي بعده. السؤال بيقول انه كيف العلماء كانوا او قدروا انه هن ياخذوا صوره للثقب الاسود. دكتور ديانا بيقول انه نعم يوجد صوره للثقب الاسود كانت في السنه الماضيه. Back at you, Dr. Dian.
So what the scientists did was take a photograph of a supermassive black hole, one that weighs the ones whose mass is billions and billions times the mass of our sun, and it sits at the center of another galaxy. This is around which the whole galaxy rotates.
Okay. اللي صار في السنة الماضية إنه العلماء قدروا ياخذوا صورة لثقب أسود موجود بمجرة ثانية. بهاي المجرة في ثقب أسود كبير. هذا الثقب عم بتدور حواليه كل النجوم والكواكب الموجودة بهاي المجرة. Right.
Now, a very good question that some of you might already be asking is, how did we take a picture of something that doesn't emit any light? What actually the scientists did was take a photograph of the matter which rotates around the black hole and is about to fall into the black hole.
Wow. فطبعا سؤالنا كان نحن انه اللي هو انه كيف قدرنا ناخذ هي الصوره مع انه الثقب الاسود ما بيعطي اي ضوء. مثل ما حكينا بالمحاضره انه الثقب الاسود ما فيه انه يبعث ضوء، فكيف قدرنا ناخذ صوره له؟ فاللي صار انه نحن اخذنا صوره للاجسام اللي عم بتدور حول الثقب الاسود، وقدرنا ناخذ صوره للاجسام قبل وقوعها يعني بلحظات قبل وقوعها ضمن الثقب الأسود. Back to you, Mr. Dale.
Thank you. And in the lecture, I explained the concept of an event horizon. This is the surface around the black hole, past which, after, if something falls into this surface, it can no longer escape. What happens is that the matter falls into the black hole, and what we have taken a photo of is the matter which is just about to fall into the event horizon.
اللي صار هلا نحن حكينا بالمحاضره وحكى الدكتور بالمحاضره عن شيء اسمه افق الحدث اللي هو سطح الثقب الاسود. فاللي نحن الصوره اللي اخذناها نحن كانت هي للجسم عند دخوله ثقب الحدث. طبعا الجسم ولما يدخل على افق الحدث، فلما الجسم بده يدخل على الثقب الاسود، لما بده يجتاز افق الحدث هون بده يختفي بعدين. فنحن اخذنا الصوره للاجسام اللي كانت راح تدخل للثقب الاسود.
So what the picture of a black hole actually shows is the matter around the black hole and a black spot in the center, which is the event horizon from which no light can escape.
فالشيء اللي موجود كان بالصورة هو المادة اللي حول الثقب الأسود، وعبارة عن المكان الأسود اللي موجود حواليه المادة. هذا المكان الأسود هو أفق الحدث اللي راح تدخل فيه المادة وتختفي ضمن الثقب الأسود. Back to you, Mr. Dale.
Thank you.
So that was the answer, right?
Yes.
Okay, well, this question actually I have also like a following question for it. Like it says, did this picture provide any evidence that supports the relativity theorem?
Yes, so it's very important that we took this photograph because we can test a lot of our predictions using it. We cannot test everything, and there is only a limited amount of knowledge we can extract from it, but it's very useful for testing our predictions.
طبعا عفوا كان بقى السؤال كان انه هل هي الصورة ساعدتنا بانه نثبت شيء عن النظرية النسبية؟ فالحقيقة الجواب كان انه نعم، الصورة هي اللي اخذناها كان زودتنا ببعض المعلومات اللي فينا من خلالها نثبت او نتحقق من نظرياتنا، وبالاخص طبعا النظريه النسبيه.
Thank you.
I have a question about like antimatter, and is there a black hole that made out of antimatter, or they only made out of matter? So I'll translate the question.
Yes.
في عندنا هون سؤال انه هل الثقوب السوداء او كيف بنعرف انه الثقوب السوداء هي مصنوعه من ماده مضاده، في شيء اسمه الماده المضاده، فهل هي مصنوعه من الماده المضاده ولا من الماده نفسها؟ Okay, Mr. Diam.
There could in principle be black holes made of antimatter. We haven't seen one and we haven't found one yet, but it's entirely possible that they exist.
ما شفنا لحد الآن أي ثقب أسود مصنوع من المادة المضادة، بس ممكن يكونوا موجودين. It's possible to exist, right?
It's possible to exist.
So, يعني ممكن يكونوا موجودين، ولكن حاليا الثقب الأسود اللي بنعرفهم أو الثقوب السوداء هي مصنوعة من المادة وليست من المادة المضادة.
In fact, there would be no external difference between a black hole made of matter and a black hole made of antimatter. As I said in the lecture, there are 3 attributes which describe a black hole.
ما راح يكون في عندنا فرق بين بين الثقب الاسود المصنوع من الماده والثقب الاسود المصنوع من الماده المضاده. مثل ما ذكرنا بالمحاضره في عندنا 3 عوامل هي بتحدد نوع الثقب الاسود.
There is mass, spin, and charge, these 3 properties. Looking from the distance, we would not be able to tell if a black hole is made of matter or antimatter. We would have to interact with it.
فعندنا نحن مثل ما ذكرنا بالمحاضرة انه في عندنا 3 عوامل هي اللي بتحدد الثقب الاسود، اللي هي الحجم، دورانه حول نفسه. So, sorry, the size, Dr. Dian, the size and the
Spin and electrical charge.
and electrical charge. وشحنة الثقب الأسود. إذا عندنا الحجم، الدوران حول نفسه، الدوران حول نفسه، وشحنة الثقب الأسود. فهدول الثلاثة هن اللي بيحددوا شو هو الثقب الأسود. بهدول الثلاث عوامل فينا نتعرف على الثقب الأسود، ولكن لما عم نطلع على الثقب الأسود من بعيد ما فينا نحدد هل هذا الثقب الأسود هو مصنوع من المادة ولا من المادة المضادة. تنعرف لازم يكون في عنا طريقة لأنه نتفاعل مع الثقب الأسود، نقدر نتواصل مع الثقب الأسود، ولكن من بعيد كل اللي بنعرفه إنه هو ثقب أسود، هل هو من مادة أو من مادة مضادة ما فينا نحدد. Back to you, Mr. Dian.
That is what I on this
all right.
question.
All right. So I can maybe also try to take another question. We have a lot of questions here, but we're running out of time. So yeah, I'll try to we have a question here that has it. Why don't they? Well, why don't the black holes suck in the whole universe?
Huh.
Well, yeah. So let me say this question in Arabic. السؤال هون انه ليش الثقوب السوداء ما بتبتلع الكون كله؟ هذا هو السؤال. So back at you, Mr. Dian.
It's a very broad question, and let me try to give some of my thoughts on it. First of all, you should not imagine a black hole as a Hoover machine.
Okay. So all right. نحن عم بيقول الدكتور ديان انه نحن ما نتخيل انه البلاك هول هو مثل يعني مكنسة الكهرباء اللي بنستخدمها في البيت. ما هو هيك. اوكي.
Instead, you could imagine it as a very hungry person.
هو ممكن نتخيله أكثر مثل حدا جوعان. All right.
In that, a black hole doesn't just suck up everything around it. It first has to prepare it.
فالثقب الأسود ما بس بيبتلع الأشياء اللي حواليه. في البداية لازم يجهزهم، لازم يحضرهم.
When a black hole finds some matter around it, it first spins it around the black hole, and that's how this accretion disk that's very bright around the black hole forms.
بالبداية لما الجسم بيكون لما بيكون الجسم قريب على البلاك هول، الشيء اللي بيعمله الثقب الأسود هون إنه يخلي أول شيء هذا الجسم يدور حواليه. Right.
And also, there is a lot of space between objects in the universe. So a black hole would only be able to accrete and swallow up the material that is in the neighborhood of the black hole.
ففي الفراغ كبير ضمن الكون. الثقب الأسود رح يقدر بس إنه ياخذ الأجسام الموجودة جنبه، بس ما فيه ياخذ الأجسام البعيدة كثير عنه. في عنا فراغ كبير بالكون وأجسام بعيدة عن بعضها بشكل كبير. Alright.
So yes, this is why we can rest assured that the very big black hole is not going to swallow up everything in the universe.
everything. Okay, alright. So عشان هيك فينا نقول نحن انه بقى الثقوب السوداء ما راح يعني تبتلع الكون كله في النهاية بسبب طبعا هالفراغ الكبير. Alright.
Let's go to the next question.
Yeah, we'll go to the next, maybe the last question. Oh, I have a question. I don't know if we answered, like, but maybe like we said something about that. Like it says, if the stars will end up to be black holes. So does that mean that the universe eventually will turn into a group of black holes instead of stars?
Well, yes, some stars, if they're massive enough, will eventually become black holes.
All right, let me just translate the question and this part of the answer. السؤال هون انه بما انه قلنا انه نجوم او بعض النجوم راح تتحول لثقوب سوداء، فهل انه بالنهايه الثقوب السوداء راح تكون او الكون راح يكون في النهايه عباره عن ثقوب سوداء فقط، راح تختفي كل النجوم؟ طبعا كان بدايه الجواب من الدكتور ديان انه بعض النجوم الكبيرة هي اللي بتتحول لثقوب سوداء. Okay, ديان.
However, at the same time, we have processes which produce new stars. So it's not like we are running out of stars. We are creating new stars every day and every year. And these stars then create their own planetary systems.
Alright. الحقيقة انه نحن صح النجوم عم تتحول لثقوب سوداء، بس كمان في عنا عمليات في الكون هي عمليات خلق او تشكيل النجوم الجديدة. يعني كل يوم عم بيقول كل يوم في عنا نجوم جديدة عم تتشكل، فنحن ما رح يخلصوا عنا نجوم في النهاية ويتحولوا كلهم لثقوب سوداء. دوما في نجوم عم تموت بالكون، في نجوم عم تتحول لثقوب سوداء، وفي عنا نجوم جديدة عم تتشكل.
And eventually these new stars would also maybe turn into red giants, or others would turn into black holes. But this process of creating new stars never stops in our universe.
Alright. فطبعا النجوم اما بتتحول ل بنسميه العملاق الاحمر مثل ما قلنا شمسنا، او بتتحول للثقب الاسود، ولكن ايضا دوما بيكون في عندنا كمان نجوم جديده عم تتشكل، فما رح يوقف. يعني مثل ما النجوم كل يوم عم بتموت، بنقدر نقول بالكون او بالفضاء في نجوم دوما كمان جديده عم تتشكل.
Thank you.
Thank you to Mr. Dian. I think, our time is over. So thanks for being with us today.
Of course, it was a great pleasure. If we have any more questions, we can probably try to answer these.
Well, I have here a question. Yeah, we can answer. Can a black hole be as small as an atom?
Oh, very interesting. Would you like to translate the question?
Yeah. If you, yeah. All right, I'll translate it. Okay, so في عندنا هون سؤال انه هل يمكن انه يكون الثقب الاسود صغير بحجم ذرة؟
So we don't know if black holes can be as small as atoms, but we know that it's theoretically possible to have so-called micro black holes, which are extremely small.
هلا الثقوب السوداء طبعا فيها تكون كثير صغيرة. Right?
Yes.
Yes, the Claudian.
Hello. Yes.
So yeah, the answer was?
The answer is that in principle, we can have very, very small black holes. They probably cannot be as small as an atom, but they can be, in theory, much smaller than, much less massive than a kilogram, say.
Much smaller than?
Much less massive than 1 kilogram. There is a unit called the Planck mass, which is the limit of how small a black hole could be in theory. So the smallest black hole could be of mass 1 Planck mass.
1 Planck mass, okay.
That my institute is named after, Max Planck.
Max Planck, yeah, yes. فالثقب الأسود طبعا ممكن يكون صغير كتير، بس قديش الحجم ما فيه، محتمل انه ما في يكون صغير بحجم ذره، بس طبعا من ناحيه الكتله فحجوم الثقوب السوداء تقدر بوحده اسمها البلانك، واللي طبعا هي مسميه على اسم العالم ماكس بلانك، واللي هو طبعا المعهد اللي حاليا الدكتور ديان عم يحكي معنا منه. الثقوب السوداء هي ممكن تكون صغيرة، ولكن ما بنعتقد إن فيها تكون صغيرة بحجم الذرة. All right, Mr. Dian, thank you.
The same principle that I explained is also valid for micro black holes. We have to concentrate enough mass in a region of space so that its escape velocity becomes larger than the speed of light.
فطبعا نحن في عندنا مبدأ تبع الثقوب السوداء انه نحن لازم يكون بالنهاية في عندنا كتلة كافية بحيث انه الجاذبية تبعها تكون اكثر من او اكبر من سرعة الضوء حتى يصير اسمه ثقب اسود.
However, it's very important to know that even though these black holes are theoretically possible, we have not yet observed them. So we know that they could exist, but we don't know if they do exist.
يعني نحن ممكن نقول انه في احتمال لانه يكون في عنا الثقب اسود كثير صغير ممكن، بس نحن ما بنعرف اذا هن فعلا موجودين. نظريا ممكن يكون في ثقب اسود صغير كثير، بس طبعا الاهم من هيك انه لحتى يصير ثقب اسود بده يحتوي كتله كبيره كثير. فنظريا ممكن يكون ثقب حجم صغير كثير، ولكن نحن نظريا بس هذا الكلام ما شفنا لسه هذا الشيء. Alright.
Yes. Let's go to the next question.
Yeah, I think we have we need to thank you here, Mr. Dian. Yeah, so I mean our time is over, so we need to stop here. And as time today is coming to an end, I would like to thank you all for participating in our pilot lecture event. Thank you, Dr. Dian, for answering our students' questions. And if you have any further questions or your questions weren't answered today, please post your questions at our Instagram page. You can see our Instagram page at the screen now. And of course, the Phoenix team will address all of them. After the lecture is finished, you will receive a short survey by email. Please take 1 minute to fill it out. We would love to know your opinion, and see you hopefully at our next lecture. طبعا بالنهاية بحب أشكر كل اللي حضروا. طبعا بنشكر كمان الدكتور ديان لحضوره ولإجابته على أسئلتنا. إذا كان في أسئلة عندكم، أسئلة إضافية أو في أسئلة ما لحقنا نجاوب عليها اليوم، ممكن بعتوا كتير أسئلة بس ما قدرنا نجاوب على الكل بسبب وقتنا، فيا ريت تبعتوا لنا اياهم على صفحه الانستغرام. اذا بتشوفوا الصفحه هي موجوده حاليا قدامكم على الشاشه، ففيكم تبعتوا لنا الاسئله، واكيد فريق فينيكس راح يجاوب عليهم، راح يبعث لكم الاجوبه. فطبعا بس بعد المحاضره نحن حابين بس ناخذ رايكم بمحاضره اليوم. فبعد المحاضره راح يوصلكم على الايميل، يا ريت الكل يتفقد ايميله، راح يوصلكم استبيان صغير فيه بس بضعه اسئله، فبهمنا كثير نعرف رايكم اليوم. فحاولوا تكتبوا لنا، او بهذا الاستبيان تعطونا ارائكم وتقولوا لنا شو في عندكم ايضا اقتراحات. بنشوفكم بالمحاضره الجاي، وشكرا لحضوركم. Thanks, Mr. Dian. Thanks, Dr. Dian. Thanks very much. Thanks for being with us today.